So as Danielle said, I've been working on fiber optic sensing, and so here what I'm showing is two images. On the right, we're looking at an instrument, a DAS, a distributed acoustic sensing interrogator, we say. So this is just the size of a computer. It's basically a computer and a laser, and it's firing into a single mode fiber. And the idea here is that we can record ground motion, that is the strain on the cable, over the length of a fiber optic cable. And so on the left, I'm showing a cable offshore Monterey Bay, where we recently connected, and we can begin to look at the first portion of the first 20 kilometers of this cable at a station spacing of 2 meters. And so that's kind of a new frontier in seismology, and there's a lot of problems that you can address with that across Earth science. Apologies, I'm going to have to change my clicker here. Okay, so what is really going on in terms of array seismology here is the ability to not just record a single seismogram, but to record the earthquake wave field, the energy of the seismic event or seismic propagating wave field at many locations. So this is not so new. We've done this in global seismology for decades, recording at many azimuths across the Earth's surface, and over time, you can see seismic phases propagating across the planet. And it's this kind of this move-out information provides velocity information. So, for instance, the distribution of seismic stations in the global sense built up 1D velocity models historically, and was used guided Earth science in a lot of ways in terms of the structure of the interior of the planet. And on the right, I'm showing a recent study by my colleague Ariel Lelouch at Stanford, showing kind of the same type of information, this spatial information about the wave field. In addition to the time axis, is the y-axis here. We're seeing distance, and this is sampling of a fiber optic cable, sampled at basically a 1 meter station spacing in a horizontal hydraulic fracturing experiment. And you can see the different phases moving out, just like in the global context, but we're shrunk down here to just less than a kilometer in the spatial dimension. And so just a little bit more about this study. I mean, what you're seeing here is the P wave and the S wave and different guided waves, which are moving through a shale layer like that, which would be hydraulically fractured. And so if you only had one seismometer, that would just be one row here, which you'd see the P wave and the S wave, but you'd miss these events, for example, this kind of scattering that is off of a fractured zone, or these other guided waves. The spatial information gives you wave number information. And so that's actually what's used to look at the velocity structure. And so you can, the amount of science that you can now do with this type of instrument at a small scale, like that of a well-field experiment, is kind of quite dramatically improved over, for example, a single station. So here I'm showing the well geometry and cross section with that shale layer, that low velocity zone, which is guiding waves. This is a simulation that Ariel ran where kind of put a source in and looked at the pink line is the DAS array, and the red lines represent the shale layer, kind of slower shale layer. And you can see this slow propagating energy here with leaked modes out into the surrounding lithology. And so this dispersive guided wave here is what's seen in the energy of the wave field with this DAS. So in terms of the kind of evolution, where DAS fits in is this as this evolution in seismic instrumentation is kind of connecting back from that global distribution of seismometers, where you'd have a very nice seismometer, an STS-1 or STS-2 at at a seismic observatory somewhere on the planet, and you'd record the wave field, and then you'd pass around the timing arrival of different seismic phases to collaborators across the world. That has kind of led to the kind of development of seismic instruments in this original form has been disseminated, and seismometers have become cheaper and easier to manufacture, with the same level of sensitivity in some cases. And so that's allowed us to deploy hundreds or thousands of sensors in large N or large nodal arrays, like that of the Long Beach array in Southern California, shown here, where you're actually seeing an earthquake, the energy of an earthquake propagate across the Newport-Inglewood Fault, or recently in the Iris wave fields experiment. There's an additional piece of seismic instrumentation that's been deployed in terms of transportable networks, the ability to set up a robust seismic recording station and achieve low noise in terms of site noise, and be able to prospect for good, quiet locations in terms of broadband recording, has kind of been demonstrated through this effort. And so in a lot of ways, DAS is kind of this just densification of this problem of recording the seismic wave field, and allowing us to then look at smaller scales, interrogate fault zones, look at environmental seismology questions, single aquifer studies, that kind of thing. But the culminating theme here is really this idea that instruments have really catalyzed this ability to do science across Earth science. So I think the kind of bottom line, a lot of times, there's the idea that we have, theory in Earth science, we have observation in Earth science, we have simulation in Earth science, but we also have the kind of instruments which a lot of times is not being focused on today. So I think that this is an important piece when we look at developing new fiber optic instruments that allow us to continue to expand on Earth science problems. So this basic question of why densify, it's really that the wave equation has this spatial component to it. So solutions provide, you can basically model the wave field better if you can record not just a time series, but that how that time series varies as a function of the spatial coordinate. And this is true in oceanography too. So we have large internal waves or buoyancy fluctuations in the oceans, which break at large changes in bathymetry, for example, here in Dongsha Island in the South China Sea. And so this is kind of a canonical problem in a lot of ways across many domains of physics. But in terms of fiber optic seismology, we've seen large growth over the last decade in terms of the number of publications on geophysics. And most recently, over the last, I would say, 5 years, there's been a real growth in many domains, like those listed here. I've worked on problems in permafrost thaw up in Alaska, and most recently problems in oceanography that I'll be talking about today in Seafloor Seismology. So the three aims that I kind of want to impart today, or three takeaways today, is this concept of what is DAS. DAS is a new technology. It's a new set of method that allows us to study seismic wave fields. So what are we actually doing? What are we recording? Secondly, I'll focus on the kind of instrument response function of DAS, which is not disclosed to us when we do an experiment with an instrument that's rented or purchased. That instrument response function is assumed to be flat, and there hasn't been a lot of detailed calibration like there has been across other aspects of seismometry. Other instruments have been very carefully calibrated before they've been sent out to the field, and DAS has been calibrated. So we have basically three themes for today. So I'm beginning to talk about what DAS is. That's the main question that I'm starting with, and I'll catch up at the end. We have basically three different types of photonics that are operating when we send in a photon into a fiber optic cable. And so these three types of optical scattering is used for sensing in across geophysics and across photonics. And so this is broadly characterized as Raman scattering, Rayleigh scattering, and Brillouin scattering. And so when we send in a photon at the incident wavelength of 1550 nanometers, that's what our laser is sending into the cable, we can record light at a higher or lower frequency, and that energy transition is sensitive to temperature. So essentially, when we send in a photon, if we want to measure Raman scattering, we can interrogate temperature. And this has been used for 10 to 20 years in terms of distributed temperature sensing as a field in environmental seismology and hydrology in particular. So here I'm plotting the wavelength axis as kind of a non-dimensional just axis, but the incident wavelength is kind of 1550 nanometers that you should be thinking about. This is very different than the kind of Rayleigh scattering that's used for DAS, where you're sending in a wavelength and measuring at the exact same wavelength. So we're not looking at frequency shifts, but we're just measuring at the exact wavelength that you're putting in. And in that sense, it's kind of like an elastic transition of the photonic energy. So you're looking at backscatter from a Rayleigh scattering type transition that is sensitive to the strain on the cable at that position. So this comes by a couple different names: DAS, distributed vibration sensing; COTDR, phase sensitive; OTDR, that's coherent optical time domain reflectometry. But broadly, these are all kind of, regardless of what you call it, this is all kind of Rayleigh scattering based measurements of strain. And Brilliant is another photonic sensing measurement where if you send in a wavelength at a given wavelength, there's transitions of Stokes and anti-Stokes, which are kind of in this Brilliant regime, which is sensitive to both temperature and strain. So I kind of put these out there because I think it's important to know that this fiber optic sensing world is a really rich landscape for geophysicists. And while I think DAS is kind of coming online as in terms of seismology, Rayleigh scattering, or DAS, is kind of coming online as the big opportunity. There's many opportunities in terms of tectonic strain or temperature changes that could be probed with these other methods in addition to DAS. So if that was, too much too quickly about what is DAS, this is kind of your takeaway slide to kind of bring you back to the Earth. We have an instrument that is, field ready, connecting to a single mode fiber, sending out laser pulses, and recording the backscattered light, that is the Rayleigh backscattered light, from every position along the cable. And that turns a single mode fiber into essentially a massive single component seismic array. So here's an example of a piece of plastic, but consider it a core of a single mode fiber. So we're going to inject a pulse of laser light, and that light is going to scatter down the entire length of the cable, according to Snell's law, inside of glass, where we're buffering the outside of the fiber optic core with a cladding that allows us to transmit the light. And so most of that light is continuing down the cable, but some of that light is scattering, and you can see that because these photons, for example, are being scattered from this azimuth back towards the camera lens, right? And so some of that light is coming out, some of the light is going back towards the source, and it's the time of flight of those photons that we're going to use for DAS. So there's actually ways to figure out exactly how much light is scattering based on attenuation inside of fiber optic cables. But this kind of details, the point of this is really to say that we're not adding anything to the fiber optic itself. We're just exploiting the natural scattering of the cable, of the fiber optic cable, as a way of probing photon backscattering. So in that sense, there's changes in index of refraction just due to the manufacturing process, which mean that when you send in light, you're going to begin to Rayleigh scatter off of any point here, and it's that transition that you're going to use as a time of flight out and back, given the known speed of propagation of laser inside of the cable. In the interest of time, I'm just going to skip through to say that strain is directly proportional to the optical interferometry phase that we're actually going to measure. So we're doing kind of like INSAR inside of a single mode fiber on every bit of light that comes back. And that's going to give us a measurement that's proportional to strain. So the way that we make these measurements in the field is by either digging trenches and laying cables in the ground ourselves if we want a particular geometry, like in this case, a 100 meter by 100 meter kind of L shape. And we make connections by using hand tools and arc fusion splicing. And we've compared different cables, different cable depths, burial depths, and looked at kind of response from vehicles largely. So for different cables, you can see there's 6 different cables laid in this trench. We saw very minor changes between different fiber optic manufacturing off the shelf, but there were really no greater increase in signal to noise in terms of the depth down to a meter. There's no greater improvement after the first 20 centimeters. So that tells you that the cable needs to be coupled. And actually, there's been cases where the cable's just laid on the ground and kind of coupled with sandbags, and that provides enough coupling to at least see some sort of seismic wave. Another way we can make these measurements is by connecting to a server, kind of fiber optic telecommunications grid or network node, like shown here. This is kind of a server rack room where we're kind of connecting to a patch panel with our DAS. And that creates a problem of knowing kind of where the fiber optic actually is under the ground. But it also allows us to record over much longer lengths. This is over 20 kilometers of length, whereas it would take, and in terms of permitting and the actual logistics of setting up such a campaign, that's pretty difficult over that kind of length. So there's been, just to put some numbers on this kind of DAS picture, we're looking at pulse widths, like I was talking about, of tens of nanoseconds. And that's allowing us to look at a gauge of this cable. So the kind of spatial resolution is around 10 meters, and that's set by the photonic process. So that could be changed, but it's often hardwired into the box. The maximum aperture, so eventually you run out of photons. So the maximum aperture that we're kind of seeing with cables, at least the standard telecommunications cables, like which are installed on the grid today, we're looking at about 30 kilometers when we kind of run into the noise of our optical budget. We can sample these data, the kind of the flow of data that comes back to us at upwards of kilohertz. The laser is firing at several multiples of that digital sampling rate. And that leads to large data volumes. So for any experiment that's going to record 10,000 components along a fiber optic cable, we're looking at a terabyte a day. And I put this kind of image from the projects that I worked on in my thesis. We were growing a massive data volume, which compared to the kind of global database of IRIS data was a large fraction. And so this becomes a problem for how you actually do data management, how you share the kind of data sets, how you even load the data sets to look at them yourself, and certainly how you standardize at the kind of large systematic programmatic level of IRIS, how this kind of transition of moving from kind of large N seismology to large N seismology with DAS is going to be a very large problem, and kind of has been pitched as a disaster from the directors at IRIS at the most recent AGU meeting. So I think this is kind of the picture of what DAS is, and hopefully that at least answers some of the questions about what DAS is. So we mentioned kind of instrument response kind of casually often as kind of knowing what how the sensor is filtering the wave field. But this becomes a really important piece for DAS, because I think that right now there's questions about what the photonics system is doing and what the fiber optic cable is doing. How will you couple your cable? And so I've interrogated that a bit with a couple of different studies. But I just want to kind of lay the groundwork by showing a couple different examples, whether we're in a well and shooting fiber size into the cable. We can look at geophone comparisons. This has been done in the oil and gas industry. and kind of compare wiggle for wiggle at a very high frequency band. In this case, well above 100 hertz, we're looking at wiggle for wiggle comparisons of the main shot at 2 different locations in this well. So the y-axis is depth along the fiber optic cable, and you're looking at the downgoing P wave. So this has also been looked at. So we've also done kind of event detection by looking at earthquakes and inside of a high seismic noise floor with vehicles moving around Sacramento in this kind of shape of array from earthquakes from the Northern California area. And so we can do lots of different types of seismology with DAS. We can do kind of earthquake seismology, imaging studies. We can do beamforming, so using the L-shape array that I was showing earlier being trenched in, the different arrivals from an earthquake are shown here in kind of rows, and you're seeing this kind of wave field arrival here. And by selectively, by kind of grid searching from which back azimuth and slowness the energy is arriving from, you can actually track a vehicle moving across the domain before the event, or seeing the body waves arriving or surface waves arriving later after the vehicle is passed. So it's kind of another opportunity to, with a single system, be able to do kind of typical array seismology. But there's also been kind of long period response down at the millihertz range inside the lab by varying the pressure that the fiber optic cable is exposed to at a cyclical frequency. We can actually see a response of the cable. So hopefully this kind of, many of these different applications in the early years of DAS have kind of asked this question of what is the instrument response function actually of the DAS. So we can consider the issue of coupling also and look at kind of a single event across many different types of coupling along the fiber optic cable in Sacramento, and see that there is differences in the response function, particularly in the longer periods. And that's kind of an interesting observation, given that basically what you're doing in the difference between the conduit here, the green trace, and the blue trace here is just adding an additional larger conduit to this cased conduit case. And you can see the amplification of the longer periods there. So this kind of question of coupling becomes an issue because every experiment has a different, even on this one experiment, we have different installation conditions of our sensor, for actually sensing element, even though we have the same photonic instrument. And so standardizing this kind of an instrument response function is important if you want to actually use the amplitude of your waveform in the end to do some sort of moment tensor inversion or some sort of science with the observation. So this is what just a kind of point of showing the kind of 20-kilometer array as a single image. This is the kind of data set that we record over 5 minutes on the Sacramento experiment. And you can see bridge resonance and kind of a distance from the road. This section of the road kind of hugs this Sacramento River here. So we're kind of far from the road. And then up here, we're near the road. So you're seeing vehicles actually travel at a known, you can actually pick out the vehicle's speed and the train speed through this area too. It's kind of locked at 5 miles per hour by permit. So there's a lot of observations you can make here, but I want to draw your attention to the actual color axis here is strain rate. So that's the measurement method. That's the kind of native measurement of this. It's strain per time sample. But the units are kind of not calibrated. So this is what's provided. This is what they say the strain is. The strain rate should be given the amount of optical phase that's being measured. But the actual observation of a surface wave, for example, with a given strain rate, does that compare to a seismometer, for example? It's kind of open question at this point. And if you actually take the DAS as a seismometer, there are kind of 3 conditions for a seismometer that we need to tick the boxes of, and those are timing. You need a stable timing. You need a known instrument response function, which is presently kind of just theorized, and you need to have a coupled sensor. So we've kind of dealt with each one of these at different times in my working with DAS, and we've kind of stabilized the clock. It's difficult to sometimes obtain a GPS signal inside of a server room, but that can be done by providing a clock time. And coupling the sensor is kind of an open question. There's a lot of numerical simulations that are being done to kind of model what the effect of the coupling could be. But in this study, I'll just look at instrument response in particular. So different instruments shown by the different curves in terms of amplitude and phase response over period are plotted. The DAS has this kind of notch at the higher end because I said we have a kind of a fixed gauge of 10 meters over which we're looking at the strain. And so that leads to a kind of a notch at the higher frequencies due to the phase velocity, which would lead to zero strain across that gauge. But at longer periods, we should be theoretically flat, and the phase response should also be flat. We have different seismic energy on Earth that we can use to probe this. For example, ocean microseisms generate energy around 7 to 20 hertz, 7 to 20 seconds, excuse me. And teleseisms provide energy down to maybe 200 seconds, 300 seconds, as recorded by broadband seismometers. And so it's this energy that I'll use to interrogate the instrument response of the DAS by co-locating a GRELP sensor. So that's exactly what we did. We took the Sacramento array, we put out a GRELP CMG3T broadband seismometer on the array, 66 meters away. There's a sensor there with a digitizer in this very nice box. So the IDAS is running, the Silixa instrument is running from here, probing the entire cable. The fiber optic cable is laid horizontally, and so we only get the horizontal component, and it's buried inside of a conduit in the ground. So we assume that this is for the wavelengths that we'll be looking at. These are at the exact same place, but that's an assumption. So here's what we see for different teleseisms. I'm plotting the seismometer velocity in gray after instrument response removal and rotation of the horizontal components into the line of the fiber optic cable. So we're looking at the same component of ground motion in gray, velocity. And then in black is the DAS strain. So I've taken that strain rate value, integrated to strain, and just converted the units from optical phase to strain. And you can see major arrivals, globally refracted phases, for example, surface waves. And for different azimuths, with respect to this cable, we're seeing different response. But this is what the DAS looks like for 500 channels over 1 kilometer of the array. And that's what the seismometer is providing, is a single trace of ground motion. And so if we convert, we need to kind of put these two measurements into the same unit. So we have strain in the image in the DAS in the background and velocity in the red trace. And so this is this kind of velocity is directly proportional to strain by omega over k. So that is the frequency divided by the wave number is our phase velocity. And so what we can do with the DAS is we can, because we have both space and time, just like if you had only a single record, you can take the Fourier transform and look at the frequency components, that would be like omega. You can do a 2D Fourier transform along the spatial coordinate axis, and that provides coefficients of frequency and wave number. And so you can multiply your strain, so you can multiply every value in this image by the frequency axis and then divide by the wave number axis and inverse Fourier transform out of that domain and achieve basically a velocity equivalent for the DAS data. And that's exactly what we do. And when we look at a trace-to-trace comparison after that conversion, so here's what the DAS spectrogram looks like after converting to velocity. And here's what the GRELP looks like. So you can see those phases kind of hitting at the same times. Relative amplitudes are different, specifically at the higher frequencies. This major surface wave arrival, including an airy phase and scattering, all kind of come in at the same phase time, but differences in amplitude are quite clear. And this is kind of the basis of, now we've basically put our data into the same coordinate system. We've removed the Geralp instrument response, so we're looking at true ground velocity. And so now the only thing that's left is kind of the instrument response of the DAS. And so if we plot these two records on top of each other, wiggle for wiggle, they do quite well. You can see the DAS velocity at specifically at higher frequencies, periods between 1 and 5 or 10 seconds, are a little bit higher. And so if we do this deconvolution, dividing the spectral amplitudes of the DAS by the spectral amplitudes of the velocity, we see a slight increase in response at shorter periods. And so the kind of conclusion of this study is that the instrument response is flat at longer periods, as supported by this example. And at higher frequencies, it looks to be slightly upshifted with a higher response, likely due to coupling. It's the current hypothesis, at least, which we need to evaluate with other experiments, see if other installations are kind of recording the same type of response. In terms of a phase velocity, though, the phase response, we're similarly flat across all period bands, at least in these 2 decades. And so that means that for timing studies, for kind of travel time tomography, for example, we look okay to be doing to be using DAS kind of just natively without kind of removing the phase velocity response. And similarly, at longer periods, we're okay to be using DAS to look at amplitude. So we can do similar things with microseism, but I'm going to move forward in the interest of time. So this is just looking at a culmination of many earthquakes. In microseism, you see that upward tick in the response. Similarly, phase being flat. So this is looking at box and whisker plots. And then if you take that instrument response function and remove it from the data, you see the kind of relaxation back down to 1-to-1 velocity response between DAS, peak ground velocity, and the actual peak ground velocity of the Earth. So the final topic I'll kind of touch on is Seafloor Seismology, an application from Monterey Bay. So I think this is kind of underscored by yesterday's event in Jamaica, large magnitude earthquake on a fault just offshore, kind of a common case actually, where we have large events in subduction zone systems or strike slip systems, which are occurring offshore. And then the amount of seismicity that's detected historically to look at the fault process, or actually be able to do earthquake early warning or tsunami early warning with this type of geometry, where we have sensors onshore and the actual fault slip occurring offshore is difficult to imagine with kind of putting down an array of seafloor seismometers or being able to use kind of seafloor GPS. So this is kind of the state of the art of marine geophysics. We have these different methods. We have kind of active source campaigns where we take out large air guns and image plate boundaries, like this in Alaska. Or we put down arrays of ocean bottom seismometers, which are kind of point sensors scattered across the whole Pacific in some cases, to look at mantle processes or deep earth kind of questions. But to actually look at crustal processes, we need kind of to densify or infill this kind of spatial axis. So one thought for kind of campaign GPS for long-term or campaign GPS for tsunami early warning, for example, or to look at changes in the kind of the tectonic timescale, would be to put down, deploy kind of a station geometry on the seafloor, and then have gliders that move around on the sea surface. And these kind of radio back the signals to give us continuous record of the data set that's being recorded on the seafloor. This is kind of an advance because the ocean bottom seismometer idea is, is fantastic and has developed to the place where we can really deploy these sensors for many months, but the data are not telemetered in real time. And so being able to record in real time means that something like earthquake early warning or tsunami early warning offshore is really a possibility. And that's really important when the fault slip is occurring offshore. There's still a latency issue though. So there's still a latency to send the signal from the seafloor to the glider to the satellite and back to shore and make a decision about what's happened. And so DAS in a lot of ways solves this problem by recording onshore with sending laser pulses out to the seafloor and recording that light back at the speed of light. We can be making decisions and cutting down that latency. So I think that's the first reason that we'd want to use fiber optics offshore to solve kind of different earth science problems. But there's this other one that's basically like we have this network of fiber optic cables already offshore, and tapping into just a small fraction of this for geophysics would allow us to answer questions without major investment, with just kind of the ability to rent a piece of the spectrum of one fiber optic cable inside of one of these cables. One could begin to study a fault that has not yet slipped and record microseismicity, for example, on that fault. So as kind of a proof of concept, actually, we, in 2018, went down to Moss Landing, collaboration between Lawrence Berkeley Lab, UC Berkeley, and Marine Monterey Bay Aquarium Research Institute, went down to the Mars cable. It's the Monterey Accelerated Research System cable, which goes out to a science node 50 kilometers offshore in about 1,000 meters water depth, and connects to a broadband seismometer sitting on the seafloor right next to it. So this cable has a number of single mode fibers, and during a period of maintenance, those fibers are not being used. So they do kind of routine maintenance for a few days. And so we were kind of sitting onshore doing a lot of DAS experiments, and we said, let's go offshore and see if we can occupy this cable and see what the data quality looked like. And kind of that was kind of motivation originally to do this experiment. But we recorded for 3.5 days, and we were really impressed by the range of processes and number of signals we saw. So it kind of led to an amazing amount of interesting observations that are now kind of opening up the way for new experiments. So in this experiment, we recorded over the first 20 kilometers of the cable, and so that's 10,000 channels at a 2-meter spacing. We used the Silixa IDAS instrument, which has a 10-meter gauge length in this case, so operating from where the cable makes its terminus at the shore. And we recorded at 500 samples per second, so that wrote out about 3.5 terabytes of data. We were able to catch a 3.5 magnitude earthquake from Gilroy, which illuminated the cable. And we have other sensors that I'll just point out now, a buoy in Monterey Bay, operated by NOAA, and the San Andreas Observatory, operated by the Northern California Earthquake Data Center and Berkeley Network. So these stations are kind of used in comparison to look at what the DAS is actually recording. I'll just point out that the cable depth here is really along the shelf. So while Mars is really off the continental shelf in deep water, we're in really shallow water of about 40 meters over the length of the cable that we were recording on. This is what it looks like. So we have the kind of Mars node cartoon here with different instruments, typically all plugged in and running and telemetering the data back out to shore. This cable is, it doesn't look like it here, but this cable is laid into, it's actually trenched with a sled into the seafloor mud, about a 0.5 meter to 1 meter depth. And this cable on shore makes its terminus here into the shore station, where we were able to just kind of connect in. There's a single mode fiber coming from this patch panel. Actually, there's the cable coming in, and it goes up into this rack and then out to our instrument here. And we can we can visualize the data with the display there. So just kind of some questions as we run through the observations. Can we use DAS to study the seafloor faults? We know we're kind of at this plate boundary between North America and the Pacific plate. And so we know that there are faults that have been mapped by the USGS, for example, in the Aptos zone. So can we see these faults? And could we study the fault properties with this type of data? So this is what one earthquake looks like over the 20-kilometer run of the cable. You're seeing the P wave as predicted from a velocity model of the crust, different phase arrivals, and then the S wave and scatters from the S, later arriving phases for the S. But you can actually begin to see variations in azimuth and also this kind of secondary scattering, which is not predicted by the velocity model for this region. So this is kind of look like point scatterers. So just zooming in on just the P wave arrival, you can see the main P there kind of weak due to the horizontal geometry of the fiber with respect to the earthquake phase velocity. But the forward and back reversal here looks like a kind of surface wave velocity of about 400 to 800 meters per second. And so that looks like a kind of single plane or single point scatterer from 3 locations that have been mapped by the USGS. So this was the kind of basis that allowed us to go to other sections of the cable and say, look, we see the same feature over here where the USGS has not mapped that. So we interpret these sections also as other point scattering faults. So this is kind of the basis for beginning to map faults on the seafloor. So we also see a large drawdown in the main arrival of the SS phase. So that is here you're seeing this kind of drawdown directly through that same mapped fault zone. And so this wavefront delay of about a half a second is likely due to the kind of low velocity structure of these fault zones. So this is the kind of ongoing work to study these fault properties with this type of energy and also the kind of ambient noise energy that we're recording. So what are we actually sensitive to? Can we see the microseism, for example? Can we see the ocean waves? What other types of solid earth signals can we see with this DAS array? So you'd be right to think that in such shallow water, the kind of waves that are crashing above or leading to a pressure on the seafloor are what the raw data set actually looks like coming into the display. So this is not bandpassed at all. This is the strongest energy. And here you're looking from 10 to 17 kilometers along the array over 5 minutes. And you can see this kind of velocity here. That's this kind of any one wave as it initiates and then comes into the cable, comes into shore and then breaks up again. The kind of peaks and troughs of strain rate as observed kind of on the seafloor. So really we're looking at the wave pressure kind of impinging on the seafloor. So there's an expression for what the pressure is at a given water depth due to some wave height as measured by a buoy. And so this kind of seafloor pressure is one hypothesis for what the DAS is actually recording. Now there's kind of the orientation question. So DAS is really sensitive to inline strains. And so with a horizontal DAS, this is kind of a vertical hydrostatic pressure. And so is that maybe a Poissonian effect that you're squeezing the cable in the vertical direction that's leading to an extension? Or is it kind of a deformation of the seafloor that leads to a stretch of the cable? This kind of requires additional calibration. Unfortunately, like I said, this is a period of maintenance, and so all the kind of instruments that could be used to address this question were taken offline for this time. So we're looking at additional experiments in the future to try and tease out what is the process that leads to this type of observation. But just as kind of a first cut, we can see this kind of connection between the surface wave height and the change in pressure. So, for example, during the 4 days, here's what the satellite significant wave height looks like. So there's Monterey Bay there. And this is significant wave height of several meters. So you can see that at the beginning there was this kind of large storm up near Seattle, and then it kind of quieted down towards the center of the experiment, and then a large storm kind of built up in the Pacific and blew into Monterey Bay by the end of the experiment. And so wave height from that buoy kind of varied in the same fashion as one would expect. But the actual spectrogram analysis from a channel of this array at 2 kilometers into the Mars array, Mars DAS array, in that kind of microseism band that we're talking about here, that this energy is represented, we can actually pick out this kind of same variability in the kind of strong energy at the beginning of the experiment, weakening energy, and then strengthening energy at the end of the experiment. So if we actually pivot the data set to look at variations in water level and as a spatial coordinate across the DAS array, and variations in wave height over the course of the evolution of the experiment, we can look at actually a fall off as shown here. So this is, the data are kind of pivoted into this axis of wave height versus water depth. So that's the color of the power of the strain. And then the model, the kind of white lines contoured, are this expression as predicted, kind of normalized to the peak wave height. So you're seeing a kind of fall off in the expected pressure at the seafloor, which if you squint, looks kind of correct for the observation of the DAS, at least kind of to first order. There is this fall off with increasing water depth. And so, like I said, this requires additional calibration, but it's kind of a first observation that DAS seems to be recording the sea level pressure that is the change in wave height above the cable. So to really address that question, what we really need is a hydrophone experiment to be able to estimate the pressure in the water column and subtract that from the this kind of solid Earth strain at the seafloor interface, and that's kind of ongoing. So what about in the microseism energy? So microseisms are kind of this interesting source of Earth noise. And so in this kind of frequency band, like I was saying, between basically 2 seconds and 20 seconds, we have the primary microseism. So that's the wave height oscillation over the kind of seafloor, the shallow seafloor near coasts. And then we have the kind of interaction between the ingoing wave of the primary and the reflected at the coast. Disaster. Sorry about that, everyone. Right, so I'm not sure how far back to go, or we're kind of at the top of the hour. I'm kind of at the end of my presentation, so maybe we can just open it up to questions.
Okay, if that's fine with you. Yeah, I mean, you were talking about the primary and secondary microseism.
Yeah.
I don't know if there's like a summary sentence you'd like to say about that, but I mean, or maybe just leave it with the how is the microseism energy partition.
Yeah, sure. I can just I'll just give a kind of a 1-minute wrap up here. I think the point is we can look at kind of variations between sensors in terms of the microseism, and actually do kind of like array techniques to kind of separate microseism, which is kind of an interesting fashionable idea from the DAS itself. We also have kind of broadband recordings down to 1,000 seconds in Monterey Bay. And so I'll just kind of leave this as kind of the summary from the takeaway. With all the audio troubles and things, I think it's better to just kind of focus on questions from here on in. But please read these 2 papers if you're interested, kind of on instrument response, and then the seafloor test in Monterey Bay, which are kind of in press now. Thanks.
Great, thank you, Nate, and thank you again for working through the audio and technical issues. So there were a couple of questions just to start that wanted to know about the cost of DAS.
Yeah, so the cost has been, so these are commercial instruments. So the cost is really the price to rent one of these instruments has been coming down, and there is an ongoing effort to kind of have academic groups test and apply the data as kind of to grow the kind of field of fiber optic seismology. But the overall cost of the instrument has been tens of thousands of dollars per month to rent the instrument. It's kind of a standard number. But there are more companies getting in the game, and there's also ongoing efforts at academic institutions and some of the national labs, like Lawrence Livermore National Lab, to actually build these instruments, kind of open source the designs of these instruments. And so there's kind of, I think I would treat it as kind of early days of the kind of cost scales, and the expectation should be that these instruments come down in price. Then again, to have 10,000 components of broadband recording in any single mode fiber is kind of an impressive technology. And so one should try and compare that to 10,000 broadband seismometers, perhaps, to look at the cost economics.
Great, thank you. Matt Fouch asks, many telecom companies are interested in DAS technology for monitoring of potential disruptions to their cables. My understanding is that DAS is currently only able to be used on otherwise dark fiber. Are there methods by which you can use DAS on active cables?
Yeah, so we've actually done some testing on this. Let me just show this kind of slide here. So we've connected an Ethernet switch and basically coupled in our DAS signal and made measurements with the Ethernet traffic by filtering the light. So that is sending the Ethernet signal, the internet signal, at 1310, and then the DAS signal at a different wavelength, which are very separated. You can record both signals without any flap of the internet connection. But I think the kind of broader question is really, could we be jumping onto any telecommunication cable like a service of to buy some piece of the spectrum of a fiber optic cable? And that has been, these are kind of early tests of this that show proof of concept, but it's a difficult enterprise to kind of it's going to be a long kind of transition to convince the telecommunication companies that this is worth the risk to their infrastructure. They're kind of a high risk industry with large financial trades and kind of piece of critical infrastructure that requires kind of continued work, I would say, in addition to kind of proving out that it works photonically, that we can see the geophysics data and see the signal. It's kind of a long transition, I would say, with building relationships with telecommunication companies, but we are kind of pursuing that.
Great, thank you. Yuri Staravoid asks, I think there was a comparison that you did with a Geralt broadband seismometer, and he was just wondering what component you used for comparison with DAS and why.
Yes, the broadband component in that case is the horizontal component of the broadband sensor. So you can just kind of surf back to this slide. So we have the azimuth of the fiber optic cable, which is kind of northwest southeast in this case. And so that's the horizontal component of the single mode fiber laid in the trench. And the seismometer here is a 3-component sensor. And so we can mathematically rotate the 2 horizontal components to extract essentially the inline component from the seismometer. And it's that inline horizontal component that we compare directly to the fiber optic cable. So those are kind of comparing the same orientation of observation inside the wavefield.
Great, thank you. Andres Garcia asks, are there any large seismic networks releasing DAS seismic data like via IRIS in addition to the seismometer data? So
this is a fun time to kind of be asking that question, because I think a lot of experiments right now are proposing experiments are kind of considering how to do that exact question. How to stream the live data. And that's a challenge at the iris level, in addition to a challenge at the kind of the scientist level, to be able to have a piece of software that sends a chunk of these data is likely a possibility over the next year. But sending a terabyte of data per day is probably not necessary. So I would say stay tuned on that, because I think there's going to be a couple of experiments coming online over the next several months that will hopefully do exactly that.